My name is Brian Kerridge. I'm the leader of the remote sensing group at Rutherford Appleton Laboratory, and we now have a group of 10 postdoctoral scientists, and we're all specialists in the field of radiative transfer and retrieval of atmospheric composition from satellite observations. So I started my career back in 1979 when I joined the University of Oxford as a doctoral student, and I had the privilege of working with some of the pioneers in the field of satellite observations who were there at that time. And what happened in the 1970s was that the first atmospheric ozone measurements were made from space by looking downwards with the ultraviolet backscatter technique, and soon after that were made profile measurements of atmospheric ozone using the LIM infrared technique, and the University of Oxford helped to pioneer that whole approach. So I was in that relatively early stage, and during my career I've watched the evolution of that whole field from the original pioneering measurements back in the mid-70s right the way through to the current day. And so I've been privileged to be able to be involved in the development of that whole field, and we've moved from initial understanding of what governed atmospheric ozone in the stratosphere, the global distribution, through to detecting and then unravelling the whole issue of the ozone hole, which appeared in Antarctica in the 1980s, and then to appreciating just how ozone actually features in the climate story as well. And increasingly, during the period of the 1990s and the early 2000s, we had a revolution in the satellite observations of ozone and related atmospheric composition. And that's enabled us to understand that story and also to begin to understand how ozone affects the climate as well. And we've learnt that ozone in the troposphere is particularly important as a greenhouse gas, and how important it is to resolve the stratospheric ozone from the tropospheric ozone where it's having that effect. So we've increased our ability to resolve in the vertical, the ozone distribution, and we're now beginning to probe what's happening in the lower part of the atmosphere, where ozone is indeed an important impact on air quality and on human health. So at the current stage, through this excellent initiative through MACC, we're at the point of being able to begin to use satellite data to actually inform our understanding of air quality and its impact on human health. And in the future, we're going to go one step further and even unravel what's happening right at the surface, where the ozone affects the ecosystem health and even agriculture. So that's the way forward from where we are now at the present time. For the MACC III General Assembly, what I'm confident in expecting is to hear a stimulating session of reports on improved understanding of the atmosphere and research and development at the cutting edge of this system, which has been established in Europe, which is in fact acknowledged to be a world-leading system of its type. Okay, well, I think what it's fair to say is that the original concept of MACC, or GEMS as it was, from Tony Hollingsworth and Adrian Simmons here, was visionary, and I think they have, and their colleagues, and indeed currently through Vincent and his colleagues, really pioneered something which is a state-of-the-art system for monitoring and forecasting atmospheric composition. And they've done that in a unique way by adopting an integrated approach. So firstly, they had the vision to see that you could build on the machinery of numerical weather prediction, which was already established, including here at the European Centre. You could build on that the system to monitor and forecast atmospheric composition and air quality. They had the ability, the technical ability, to set up the machinery through data assimilation to be able to integrate all different types of satellite observation along with surface observations, and to integrate with the NWP system the complex processes of chemistry and surface emissions. So those are considerable technical achievements, and I think going forward into into the Copernicus Atmosphere Monitoring Service, we expect to see further innovation, further development, and to retain this cutting-edge capability in the European system. Okay, well, I think what we can expect is for the Copernicus Atmospheric Monitoring Service to benefit considerably from advances on the satellite observation system. We have in prospect in the next decade some really important continued advances in the satellite observation system, coming from firstly from the geostationary perspective, introducing from METOP 3rd generation and Sentinel-4 the ability to look down over Europe and to monitor trace gases such as nitrogen dioxide during the course of the day, so it will be able to be possible to look at the emissions as they appear during the day and so on and so forth, which is vital for air quality forecasting. Then, on the global scale, we have the advances from METOP 2nd generation and Sentinel-5, where we're going to have much increased spatial sampling, much increased spatial resolution, and that will enable us to pinpoint the emission sources and the impacts of pollution, and that will feed into the machinery of the CAMS system for forecasting and monitoring. And the third thing we'll have also on METOP 2nd generation will be much improved information on atmospheric aerosol by having the multi-angle, multi-wavelength, multi-polarization imager, and that will give us much more information on aerosol properties than just the total optical depth through the atmosphere. So really, all in all, I think CAMS will be able to benefit considerably from this advances on the observational side in Europe. And in parallel with that, no doubt, will be advances on the modelling side. Again, increased resolution to better represent the processes, and that will lead to more accuracy and better understanding. And in particular, what I'm hoping is that the very complex issue of composition-climate interaction will be better understood, enabling us to predict more confidently what will happen with the future climate and composition system. Okay, this is a question where I'm not so expert. My personal view on this is that at the moment MACC has established a world-leading position in this type of system, and that could be of benefit to the broader international community as systems are set up in other countries. So it goes without saying that that would be a value. I think in terms of learning, there are things that the MACC community or the CAMS community will be able to learn from the American side and elsewhere. So of course international collaboration always is fruitful, and in the past has seen lots of advances through that means. Okay, well, during my career I've had the privilege of being involved in a number of advisory groups for the space agencies and also for the EC in looking at the space infrastructure that was needed for the Copernicus Atmosphere Service, and a lot of advances are going to come forth, as I've mentioned. There's one gap which we will have in the future, and that is for the adequate profiling of stratospheric ozone and related constituents. And so going forward, what we're lacking is a limb sounding capability in Europe and indeed worldwide to enable us to get the proper picture on the vertical structure of not only ozone but other constituents in the stratosphere, and as well as giving us the necessary information for long-term monitoring. That will also enable the lower atmosphere to be better characterized, in the sense of, in the integrated system, if you can represent the stratosphere accurately, then that enables you to use the total column measurements from downward viewing sensors to better inform the troposphere. And I think at the moment that's one remaining gap that's still to be resolved by the agencies and the community. So I'd like to ensure that that kind of gap is filled in the future. it's a little bit of a puzzle as to why that gap is still outstanding, in the sense that a number of international committees and even the working group for the Copernicus Atmosphere Service Space sector, they all identified this as being a gap. And it's a little bit of a puzzle, but I think it is to do with the fact that it's never inexpensive to launch a satellite mission or a series of satellite missions, and yet this is one step removed from what people on the surface of the Earth experience in general. So people on the surface of the Earth are concerned about their immediate environment, their air quality, and so on and so forth. They're concerned about ozone only in respect of they're concerned about stratospheric ozone in the effect that it protects them from the UV radiation, but other than that they don't give it much attention. So I think it's a kind of part of the system which has been not given the priority that in the long term it will need in order to ensure we have an holistic system that addresses the whole problem. Okay, so some of the recent highlights within MACC have been undoubtedly the work which has been done on characterizing methane globally from space, and to use that information to better understand and quantify the emission sources of methane. And that's been really impressive because of the rather small fluctuations in the methane distribution that you need to be able to work with to achieve that, which are the few percent level. So that's been a real kind of major achievement. And looking forward, the ultimate goal would be to achieve a similar achievement with carbon dioxide, which has yet smaller deviations from uniform mixing around the globe. So that's been a kind of holy grail for the community, and with a new American instrument which has recently been launched, OCO II, there's a new opportunity to address this issue and to determine whether the tiny fluctuations in carbon dioxide can be used to monitor the surface emission sources of CO2 and also their sinks. And so I think this is a real exciting opportunity, and that's emerging at the moment along with future Japanese and Chinese missions. So looking forward to the operational phase upcoming, it will be vital that the team continue to maintain their momentum on research and development in order to innovate further all aspects of this system and to enable it to evolve and improve in terms of accuracy and also in terms of the range of new applications and services. I mentioned earlier the issue of ozone near surface, and if we can begin to, with this system, establish what's happening worldwide at the ground with ozone, that will help us understand the processes whereby ozone affects ecosystem health and indeed affects crop yields. So that's one example of the way forward, I think. Going forward into the new operational phase, it will be vital that the team continue to develop and innovate the system in order to stay at the cutting edge internationally and to improve the accuracy of their products and services, but also to extend the range of services. So it's absolutely vital that research and development in this operational phase remains front and centre. One other way in which MACC has successfully shown the power of integration is to be able to combine the global right the way down to the regional and further down through the downstream services indeed to the local air quality forecasting. So what that does is it brings to the citizen the ability to have air text service which tells them what the daily levels of pollutants are likely to be and whether or not they should be concerned. That service is building on the entire panoply of the MACC system, from the global and the satellite data going in at the front end right the way down to the individual on the street or indeed in their home. So I think this is truly impressive, the way this integrated approach through MACC has yielded new applications and services for the citizen of Europe.